All right, and then to round off and finish up our introduction to chemical compounds, the last one is metals and metallic bonding. It's not something that we go into a huge amount of depth with normally in this course, but I do want to do it for completion's sake because we did have covalent and ionic. Metallic bonding, to review what we talked about originally in the first video, is that it's a bond formed between just metal atoms because they all have relatively weak attractions for their valence electrons. So when we have multiple metal atoms next to each other, those valence electrons aren't really tightly bound to any one of the atoms and instead kind of exist in between all of them and moving around freely between them in something we call and refer to as the sea of electrons. So as these valence electrons are free to move around in this way, it leaves behind these metals as cations themselves because they don't technically possess that valence electron anymore. And those positive cations then attract to this sea of electrons, kind of binding it all together. You could think of it almost like when you take, you're baking and you mix a lot of flour into water, and the water helps bind all of the flour together, even though it's not really chemically bonded in the sense. As a diagram picture, we can see here we have an example with aluminum. So this is what happens, for example, in aluminum foil. We have a whole series of aluminum atoms here next to each other. And in yellow, we have the valence electrons kind of highlighted. But when they're all together, since an individual aluminum atom here cannot tightly bind or bound and hold on to these valence electrons, they're free to kind of exist between all of the aluminum atoms here. So these positively charged nuclei cores of the aluminum are able to attract to that negative, right, because all of these are negative electrons, this negatively charged sea of electrons in between them all. Now, again, compared to our other two compounds, this makes, again, some really unique properties because unlike ionic bonding, we don't have a really strong attraction of individual ions locking everything in place. And unlike covalent bonding, we don't have these unique and individual molecules that are loosely connected to each other. We have a whole third different type of compound. So from this, we get the unique properties of metals, of their extremely high electrical and thermal conductivity in all states of matter, whether that's solid or liquid, usually not gas because they don't really boil very readily, but it can happen. And unlike in ionic compounds, these mobile charged particles aren't ions themselves, but rather it's the electrons, since they're free to move throughout the whole solid. If electrons or electrical current is added to one side by a battery, the electrons here can enter into the metal and they'll just keep pushing the rest of the electrons out the other side. And we have this rapid flow, rapid transfer of electrical current. Similarly with heat and thermal conductivity, if we heat up one side of the metal and we make those electrons start moving really, really rapidly, they can rapidly move through to the other side, which is going to make the temperature on the other side increase really, really rapidly. Right? High conductivity. Again, because of this loose binding of all the particles together, thinking like our bread dough almost, metals have a property of what we call malleability, which means that they're able to be bent and shaped and deformed as we apply forces to them. And that's because these metal atoms are able to slip and slide past each other while maintaining this attraction to the negative electron cloud in between, sea of electrons in between them all, since it's not as rigid as the ionic crystals would be. Similar to malleability, we have another property called ductile or ductibility, and that's their ability for metals to be drawn apart, stretched, and shaped in that way rather than being pressed and formed. So this is like when you form a wire. Again, because we don't have the rigid structure of the ionic crystal, they can be reshaped in that way. And then another common property is metals tend to all have this similar color, this silvery color, and they have a high luster. Right? They shine. And that's because as light comes in, it can excite the electrons in that sea of electrons, sending them to higher energy levels, as we talked about back with fireworks. And as they drop back down, they emit and reflect that light back out very, very readily. This doesn't tend to happen as much in nonmetals because those electrons are much more bound into their molecular shapes or their ionic crystal shapes. whereas in metals, they're much more freely moving. Now, metals themselves, pure metals are great. We do a lot of stuff with them, aluminum foil, iron, metal. But for a lot of practical purposes, we have to end up making what are called alloys, which are mixtures of metals. Because different metal atoms have different shapes, they have different levels of attraction to those electrons. By mixing them and combining them in different ratios, we can actually tweak the properties of metals to make them more practical for different purposes. So for some examples of alloys that are common, is copper and zinc are put together to make brass, or copper and tin are put together to make bronze. For example, copper is generally a very soft metal, and when we add some tin to it, that overall alloy becomes a lot harder. Hence the Bronze Age, when those first metal weapons were started to be made, bows and spears and that kind of thing. A lot of musical instruments and bells are made out of brass, copper, and zinc, because if they were made of just copper, when you hit them, they would just dent and deform, which would not make a very good ringing sound. If you put too much tin into it, it becomes too hard, and it makes just a high-pitched kind of ding sound. But to get that nice reverberating sound that you think of when you hear like a bell ringing or a trumpet playing or something like that, we end up with that mixture of copper and zinc together. On the right, you see a table here of some different types of metals. Any of you planning to go into engineering for either material science, civil engineering, mechanical engineering, anything of that kind, you will have entire classes devoted to just specific metals. For example, steel has an entire course because there's so many different types of steel for different purposes based on the combinations of metals that are put into the different alloys. Between alloys themselves, there are two different types. One's called substitutional, which looks almost like an ionic crystal, where we just have alternating metal atoms of different types. So, for example, 14 karat gold, which isn't just pure gold. It has to have other things in it, in this case, silver. But steel itself is a different type of alloy called interstitial, where instead of having iron alternating with carbon, because we see just iron here, because iron is so much bigger than carbon, the carbon actually squeezes in between the iron atoms into that empty space as those spheres pack together to make the overall shape of the metal. And again, another example of that as to how the alloys tweak the properties. As carbon gets put into iron to make steel, we know that carbon, since it's non-metal, attracts those electrons to a much greater degree, binding them and holding them in. So the more carbon there is in the metal, the less malleable, the less ductile, and the less able to be deformed the metal becomes. Right? So higher carbon makes it become harder, stiffer, springier, etc. So here, this table on the right is taken from one of those Steele's classes textbooks, and we see that as the percentage of carbon increases, we get to much harder examples and uses of the metal. For example, drills have really high carbon steel, but wires have really, really low carbon steel. An at-home example of this would be something like a bobby pin, where it's springing hard. To deform it, you have to use a lot of force. Whereas a paper clip is low carbon steel, you can easily bend that and shape that and do whatever you want with it.